All right, everybody, welcome back to yet another installment of Chemistry Knowledge. So last time I was looking at you guys, you were learning about moles and like what they were and how we use them and how to convert grams to moles and learning all about the roadmap and stuff like that. So today we're going to learn one more thing, which will wrap up this chapter, and it's all about stoichiometry. It's a really weird word, but really all stoichiometry means is the study or like looking at or working with numbers. That's all that means. So what we learned before was how to go from like moles to numbers and moles to mass, and then mass to moles to numbers and numbers to moles to mass. We did all that kind of crazy conversion. But now what we're going to do is like one last thing. It's going to connect the amounts of one substance to the amounts of another substance in a chemical reaction. For example, if I have 5 moles of hydrogen, how many moles of oxygen do I need? Based on this chemical equation in front of you. It's basically when you go from moles of one thing to moles of another thing, right? From moles to moles. So it's not like there's no gram formula mass. There's no like Avogadro's number. So we're going to dig right into it. We're going to learn all about like mole to mole ratios and how to go from one thing to another. And we're going to learn what the big word stoichiometry is all about. Don't be scared. Okay, here we go. First things first, guys. Stoichiometry. What is it? It's what we're going to be talking about today. It's basically calculations based on coefficients. The word stoichiometry, like this part, the stoichi, that just means numbers. And then ometry is like the study of or like working with. Right? So it's just like the study of or working with numbers. That's all stoichiometry means. And for us, in chemistry, it's going to be calculations based on coefficients from a balanced chemical equation. Now, this is where we make the connection between the number of particles of some... I hate that. So we're just going to go from moles of like one substance to moles of another, whether we're going to figure out how much we need for the ingredients to make it work properly, or if we're going to see like if we start with so much reagent, how much product, like, or reactant. If we start with so much reactant, how much product do we make? We'll see. All kinds of different ways to go back and forth. So here's how it works, right? The coefficients, right? You guys remember what like coefficients are, right? Coefficients are these, right? That one's 1. It's the big numbers in the front of the chemical formulas, right? So the coefficients are used to determine the number of moles in a reaction, right? So like we did earlier, like 2 molecules of hydrogen and 1 molecule of oxygen produce 2 molecules of water, right? And we can switch that with our language straight to moles, right? So 2 moles of hydrogen molecules and 1 mole of oxygen molecules produce 2 moles of water. So what you just got was your mole ratio. Remember I had you guys keep looking at these things, at these big numbers? Well, this is why, because the ratio for hydrogen to oxygen is a 2 to 1. So we need 2 moles of hydrogen for every 1 mole of water. Does that make sense? Or you could think of it this way. For every 1 mole of oxygen that you add into your like reagents or into your reactants, you will produce 2 moles of water. Do you guys get how that works? Awesome. So here are some basic questions that we'll start with. Some basic problems using stoichiometry. So here's what it looks like. How many moles of oxygen are created when 0.4 moles of potassium chlorate decompose? Here, let's get a different color. I'm going to go with purple for right now. So the first thing we have to do is balance this chemical equation. 1 potassium, 1 potassium, 1 chlorine, 1 chlorine, 3 oxygens, 2 oxygens. So the least common between the two of them is going to be 6. So I'll put a 2 here, and I'll put a 3 here. So that's 2 times 3 is 6 oxygens. 3 times 2 is 6 oxygens. Got to go back to start all over. 2 times 1 is 2 potassiums. I'll put a 2 here, so 2 potassiums. 2 times 1 is 1 chlorine. 2 times 1. 2 times 1 is 2 chlorines. 2 times 1, 2 chlorines. All right, we're all good. So we're balanced. So the first thing we need to do is to determine the mole ratio. Then we're going to use dimensional analysis, or what we like to call lines of pain. And stoichiometry, which is going to be nothing more than a mole to mole ratio. That's all stoichiometry is going to be for us. Nothing more complicated than that, right? So let's go to this equation and see again what it's actually telling us. It's telling us that we need 2 potassium chlorides. We will make or yield 2, wait, that's potassium chlorate. We will make 2 potassium chlorides and 3 oxygens. You got it? Okay, so the question, also this is another thing I like to do. Again, like, word problems are terrible, especially if your eyeballs want to be like hateful and dyslexic. So what I end up doing is I go here and I underline or circle lots of things. How many moles of oxygen? This is what I'm looking for, right? So I write it down. Moles of O2 equal question mark. That's what I'm looking for, right? And if I do that, if I like write it down, it no longer becomes a word problem. Now it's just like a regular old math problem if you write it down. Got it? Great. Okay. Are created when 0.4 moles of potassium chlorate decomposes. So that's going to be 0.4 moles KClO3. Okay. Guys, it's no longer a word problem. I got to get to moles of oxygen from moles of KClO3. So I got to go from here to here. All right. So the first thing we need to do is to determine the mole ratio, and here's what it is: 2 KClO3 to 3 oxygen. Now, where did I get that from? From right here, remember? Like right here from the chemical equation. I need 2 KClO3s, and I will yield 3 O2s. So the ratio is 2 moles of potassium chlorate to 3 oxygens. Right? 2 KClO3s to 3 oxygens. Just like that, it's a 2 to 3 ratio. Does that make sense? All right, so part 2, I'm going to use the lines of pain and I'm going to use dimensional analysis, lines of pain, and stoichiometry, the mole-to-mole ratio. And your mole-to-mole ratio is this guy right here. 2 moles of KClO3 is equal to 3 moles of O2. Got it? And where did I get this mole-to-mole ratio? Right from here. Dig? Okay. So, why did I choose KClO3 and oxygen? Because that's the 2 things that I'm looking for, right? These are the 2 substances that I'm relating, going from one to multiple. And I got it from the question. Dig? So, I write down what I'm starting with in the upper left, right? I draw my lines of pain. And if I have moles of potassium chlorate in the upper left, I'm going to need moles of potassium chlorate in the bottom right. Now, how many moles of potassium chlorate? Well, according to my mole-to-mole ratio, I will need 2 moles of potassium chlorate. And then up top, I'm going to need moles of oxygen. How many? Well, according to my ratio that I got from the chemical equation, I'll need 3 moles of O2. Got it? So before I start mathing, I need to make sure that my moles of KClO3 cancel my moles of potassium chlorate, and I need to make sure that I'm getting the units that I need to get. So let me go back to my question and double check that. Ah, yes, right here. Moles of O2, that's the question. That's what I'm going to get. The math will end up being 0.4 times 3 divided by 2. So that'll be 0.6 moles of O2. You guys picking up what I'm putting down? Sweet! Let's try one more. How many moles of NaOH are needed to completely react with 2 moles of H2SO4? Well, I'm not given anything here at all, so it looks like I'm going to have to make my own chemical equation there. But I ain't scared of you. I think I've done this before. All right, so here we go. And the salt. By the end of the year, you're going to be able to do this all on your own. How? Trust me. All right, so let's see what we got. Let's balance this bad boy. We got 1 sodium, 2 sodiums. So I'm going to put a coefficient of 2 right there. All right, and I got 2 sodiums all over the place. The next thing I got, oh boy. So now I'm looking at oxygen here, but oh wait, this might not be too bad. Because look, this is oxygen, this is SO4. Okay, for a minute there I was a little freaked out because I've got oxygen right here and I've got oxygen right here. Oh, don't like that when oxygen is in 2 places. However, dude, this is an SO4, so this is going to be one thing. I've got SO4 on that side and I've got SO4 on that side, so no worries. Okay, so let's check this out. I've got 2 oxygens here. I've got 1 oxygen there. I'm going to put a big fat coefficient of 2. And now I've got 2 on each side. Let's start over. 2 times 1 is 2 sodiums. 1 times 2, 2 sodiums. 2 times 1 is 2 oxygens. 2 times 1, 2 oxygens. Very nice. Now I've got, okay, now this one's ugly. I've got hydrogen here, and I've got hydrogen here, and I've only got hydrogen in one spot. I'm skipping it. I can't, no, let's just see what else happens. So let's come to I don't want hydrogen, so let's skip it and go to SO4. I've got 1 SO4 here, I've got 1 SO4 there. All right. I guess let's do, I guess we have to go back and check hydrogen. 2 times 1 is 2, and 1 times 2 is 2. So in all, I have 4 hydrogen atoms in all on the reactant side. Now on the product side, I have 2 times, I got all scared for nothing. 4 on each side already. Okay, that was easy. I got scared. I'm not going to lie, man. I got all intimidated because hydrogen was in 2 spots. It frightened me. So there's my balanced chemical equation, and I can't remember. Okay, how many moles? Okay, here's my one thing. How many moles of NaOH? That's one thing I need, so I'm going to write it down. Moles are needed to completely react with 2 moles of H2SO4. Alrighty, so there we go. So the 2 things that I'm going to be messing with here are NaOH and H2SO4. Right? So what I'm going to do is I'm going to write down what I'm starting with in the upper left-hand corner, which in this case is 2 moles of H2SO4. Got it? Now I'm going to put that in the upper left-hand corner of my lines of pain, and I'm going to make my mole ratio. Well, let's see here. I'm going to do my mole ratio. Maybe I'll write it up here. I have 2 NaOH. Where did I get 2 NaOH from? Right there. Is equal to or equivalent to 1 H2SO4. Digged it? Dugged it. All right, so now I'm going to take this ratio and pop it in on this side, and if I have where'd my thing go? If I have H2SO4 in the numerator in the upper left-hand corner, that means I need H2SO4 on the bottom right in the denominator. And according to my ratio, it would be 1 H2SO4. That means on the top in my numerator, I'm going to need 2 NaOH. And this will be moles of H2SO4. Okay, moles of H2SO4, moles of H2SO4. I'm left with NaOH. Ooh, yep, I do want NaOH. So it'll be 2 times 2 divided by 1. That's how many I need. Makes sense. It's twice as many, right? Because if that's 1 and that's 2, it's like double. Like I started with 2, double 4. Sweet. Let's see. Show the following equations to follow the law of conservation of mass. All right. So I guess we're going to have to balance this bad boy first. Whew. 3, 2, then I put 2 here to make 6. I put 3 there to make 6. So I have to start all over. 2 times 2 is 4. All right, let's make that clean. 2 times 2 is 4. 4 times 1 is 4. 2 times 3 is 6. 3 times 2 is 6. Yay! Show the atoms balance. There, I did that. So the mass on both sides is equal. All right, well, I can do that. So if I've got Al2O3. I'm going to quick find the gram formula mass for one of those bad boys. Okay, so what I'm going to do here is find the gram formula mass for aluminum oxide. Okay, so let's see what we got here. Al. But there are two of these big guys, so I'm going to do 1 times 2. That's a little bit better. Now this guy over here for aluminum, we've got 4 times 27. All right, and for oxygen, I've got 3 times 2, that's 6 times 16, that's 96. So 108 plus 96 equals imagine that, it worked out finally. All right, got it? Awesome. So the next one, how many grams of carbon? This is a big one, guys. This is like kind of, this one is like kind of pertinent to everybody. So let me see if I can get this. How many grams of carbon dioxide are produced from 1 mole of gasoline? So this is gasoline. So the first thing we're going to need to do is balance this bad boy. All right. So 18, so that must be a 9. 2, 8 times 2, that's 16, and 9, that's 25. Can't make this into 25 because of that, because like it's only going to be even. Okay. I don't know if I can make that work. So I'm going to go back and start with 2 of these bad boys. All right, so 2 times 8 is 16, so I'll put 16 carbon dioxide. What is that? 2 times 2, 2 times 18. Here, oxygen, 2. What is 16 times 2? 32 plus 18. All right, now it's nicely balanced. Delightful. Okay, there is my balanced chemical equation. So we want to know how many grams of carbon dioxide are produced from 1 mole of gasoline. All right, I think I know how to do this. I'm going to write what I start with here, 1 mole of gasoline, right? And then I'm going to do my lines of pain. And then I need to get my mole ratio of gasoline, which is going to be 2 gasolines for every 16 carbon dioxides. And since I have gasoline in the upper left, I'll put 2 gasolines down here. And I'll put 16 carbon dioxides here. So that's going to leave me with 8 moles of CO2. Done, right? Let me double check here. Grams of CO2. Okay, so I need to find grams of CO2. But this, oh, no, not done. I'm not done yet. All right, I almost missed that myself. So it's asking for the answer to be in grams, but all I've got right now are moles. So you take the moles of carbon dioxide, you pop them in the lines of pain. You dig? And now we need the gram formula mass of carbon dioxide. Let me think. 44. So if carbon dioxide, that's the gram formula mass. Let's do the math real quick. It is. If I have moles in the upper left, I'm going to want 1 mole in the bottom right, and I'm going to want 44 grams in the in the numerator, in the top there. So let's double check here. We got moles canceling out moles. I'm left with grams. The math is going to be 8 times 44 divided by 1 equals 352 grams of CO2 from 1 mole of gasoline. Doesn't seem like a problem. All right, guys. That is just about all we've got for today. And as far as the things that we do for practice in class, I haven't quite decided yet. It's probably going to be something like stoichiometry or stoichiometry part 2. I don't know. I haven't really made up my mind yet. So we'll figure it out when next time I'm looking at you. So I hope you guys have an awesome, super day. I know I'm going to. And give me a few. All right, guys. Thanks for being genuinely awesome. Have a good